magnetic field due to a toroidal solenoid or toroid. In the diagram, this is a toroid and this is a ring on which an insulated metallic wire is wound in this way. Now the wire is wound in this way, and we get a solenoid which is bent in a form of ring. R is the radius of this ring, OB the center, and we consider a point P. We consider a point P we consider a point P on the axis of this ring or on the ring, and at the point P, magnetic field B acts tangentially. At the point P, magnetic field B acts tangentially, as shown in the figure. As shown in the figure. A toroid is an endless solenoid in the form of a ring. A toroid is an endless solenoid in the form of a ring. That is, it is an anchor ring. It is an anchor ring or torus. That white color ring is anchor ring or torus, around which an insulated metallic wire, or around which a large number of insulated metallic wire a large number of tons of insulated metallic wire are wound. It is used as an inductor in an electronic circuit, or in electronic circuits, especially at low frequency, where comparatively large inductances are necessary. Now we can draw the diagram of toroid. Let B be the magnetic field induction, or magnetic flux density at the point P, as shown in the figure. At the point P, on the anchor ring of the toroid, B is the magnetic field induction or magnetic flux density at the point P inside the toroid at a distance r from its center O. Now in the diagram, B is the magnetic field which acts tangentially. B is the magnetic field at the point P, and R is the distance of the point P from the center O. And this is what a toroid. This is a toroid, and this white color ring is anchor ring, on which a large number of tons of insulated metallic wire are wound. This is insulated wire. I be the current which is flowing through the toroid as shown in the figure, and the current flows away from the toroid. This anchor ring on which a large number of turns are wound, and we get a ring-shaped solenoid. When a solenoid is bent in the shape of ring, that is called toroid. That anchor ring is also known as torus, on which a large number of tons of insulated metallic wire are wound. This is the diagram, and B is the magnetic field induction or magnetic flux density at the point P inside the toroid at a distance r from its center O. Hence, B is the magnetic field induction at the point P inside the toroid at a distance r from its center O. According to Ampere's circuital law, the line integral of the magnetic field induction or magnetic flux density, magnetic field induction B, vector B, which acts tangentially on the anchor ring of the toroid, So if we draw the diagram of toroid again, so this is the anchor ring on which a large number of tons of insulated metallic wire are wound. P is the point on the ring of toroid. At P, magnetic field induction vector B acts tangentially, and we consider a small element of length dl, small portion having length dl on this anchor ring, and this dl, small length vector dl, will be acting tangentially. That's why vector B is parallel to vector dl. Vector B means magnetic field induction vector will be parallel to vector B, and wire is wound in this way. That means a solenoid is bent in the form of ring. A wire is wound on that anchor ring or torus in this way, and we get the toroid, and this will be the radius of the toroid. This is R, or radius of the toroid, and O is the center of the toroid. And according to Ampere's circuital law, the line integral of the magnetic field induction vector B, which acts tangentially at the point P inside the toroid, is given by, which acts tangentially at the point P inside the toroid along the circular path of the radius r is given by closed integration vector B dot vector dl is equal to mu 0 ni. Closed integration vector B dot dl equal to mu 0 ni, and this is equation 1, where here I is the current which is flowing through the toroid. I is the current flowing through the toroid, and Ni is the total current. Ni is the total current threading the ring. Ni is the total current threading the ring. Also, Ni is the number of turns. Therefore, close integration BDL cos 0 degree equal to mu 0 Ni. Under bracket, as vector B is parallel to vector dl, that's why theta equal to 0 degree. Magnetic field induction, B can be taken outside, B integration dl equal mu 0 ni. Therefore, B 2 pi r mu 0 ni, where integration dl is a circumference of the ring of the toroid, where integration dl equal 2 pi r, which is the circumference of the toroid, circumference of the ring of the toroid of radius r. So this is the anchor ring or torus, and r is the radius, p is a point, and vector B is a magnetic field acting at the point P. And integration dl is equal to 2 pi r, which is the circumference of that ring. So B equal mu 0 under bracket n divided by 2 pi r bracket close into I, or B equal mu 0 small ni, B equal mu 0 small ni. This is the magnetic field induction or magnetic field induction or magnetic flux density. At the point P, inside a toroid, where small n is equal to total number of turns n divided by 2 pi r, which is the number of turns per unit length of the toroid, which is the number of turns per unit length of the toroid, magnetic flux density